Hello, welcome back. This is Dr. Oz from Western Kentucky University. So today we're going to work on an application of differential equations. In particular, we're going to work on the compound interest problem. I just want to remind you at this moment that we have certain differential equations spitting out solutions in the form of exponentials. Here I just want to bring this slide back for you to remember exponential growth and decay problems. If you have a differentiable function of t such that y is strictly positive, but the rate of change of y in time is proportional to y itself, and the k here is the proportionality constant, so because y and dy over dt are proportional. And those differential equations, through the application of separation of variables, would have the general solution in the form of an arbitrary constant times the exponential kt. And here c is the initial value of y, and k is the proportionality constant. And depending on the sign of k, either you have the growth or decay problems. And I want to relate this to our application problem for compound interest. And let's just read the statement of the question. Let's say like you have the initial amount of $1,500 to be invested for your savings account, and then the annual rate is 8%, and you're trying to investigate the shortest way to double your money. Should you just compound the money annually or monthly or daily or continuously? So sort of like we're going to investigate each case and see what's going on, but just to give you some heads up, the continuous compounding question is the one that I mentioned about the exponential growth or decay problems in the previous slide. So that's why when we compound the initial amount continuously, the solution is always in the form of exponentials here. So if you compound, let's say daily, so you just put your money into the bank, and then the next day you get an interest just for one day, and then you get that interest added to the initial amount, and then that amount is now your initial amount till tomorrow. So that it compounds till tomorrow, and then you get the interest for the second day as well, and now you just collect all the money and then compound it again daily, or monthly, or quarterly, or annually. But these are all discrete versions of the differential equations that we're talking about, so that only the continuous case would have the exponential type solution, but the discrete case is always coming out of some number to the power of n to the t, and that number is not e. However, if you sort of like let n go to infinity, n is the number of compoundings through the year. If you let that n go to infinity, so that means you are compounding infinitely many times during the year, that is supposedly converging to what I call the solution in the previous slide for a differential equation. So let's start with the annual compounding, and we have the solution already given in this form. And since n is the number of times during the year that you compound the total accumulated money, since we are talking about the yearly compounding, so n is going to be 1 for part A, okay? So n is going to be 1 to start with for the annual compounding. And r is the given rate anyway, so that's fixed, 0.08. And the initial amount is $1,500, and the final amount that I want to reach to is $3,000. In other words, I want, in this case, because this is also corresponding to, this solution corresponds to the annual compounding, so I want x to be 3,000 for some time, which I'm after. Okay, I start with 1,500, and 1 plus just 0.08. I don't divide it by 1, right, because it's still 0.08. And then this is just 1 times t, that's exactly equal to t. Okay? So again, our goal is to determine t here. So why don't we divide both sides by 1,500, so that you have 2 on the left and 1 plus 0.08 t to the power t on the right. Well, to solve this equation for t, we remember something from pre-calculus. We take the ln of both sides, okay? So ln2 equals 1 plus 0.08 ln times t. Normally t goes down, so you have ln of 1.08 times t. So in turn, t is going to be ln 2 divided by ln 1.08. Okay, this is something that you can use your calculator for, and you get 9.0064 years. If you don't touch your money for the whole year, and if you just keep compounding annually to reach $3,000, you should wait 9.0064 years. Now let's change this to monthly. Monthly means like we have 12 months in a year, so we're going to compound it like 12 times during the year. So in other words, n is going to be 12 now. N is going to be 12. Okay, so let's just rewrite this whole thing for n equals 12. All right, the goal is still having $3,000. And then now I have the interest rate to be still fixed 0.08, but I do compounding 12 times. And this time I'm going to multiply t by 12. So now I have another equation to solve for t. I'm going to use the same methodology. First, I'm going to divide everything by 1,500 so that I have 2 left here, and then this whole chunk, 0.08 divided by 12 to the power of 12t. And the solution technique is exactly the same. I'm going to take the ln of both sides. ln 2 equals 12t times ln of this whole chunk. Okay? And t comes out of this division here, ln 2 divided by 12 ln of 1 plus 0.008 divided by 12. Okay, there's no fraction here. This is just 0.08 divided by 12, by the way. Okay, so if you use your TI-84, let me just copy from my notes. This is equal to 8.69 years, which is a slightly better number because you reach $3,000 in 8.69 years, which is earlier than the one compounded annually. That was in fact around 9 years. Okay. Let's look at the third case, which is daily. Daily means like we have 365 days, so n is going to be 365. At this moment, I want you to do the calculation by yourself. Okay, and I'll just provide you the final result. So n is going to be 365. So this is 365 and 365t. And I want you to apply the same strategy. We're going to find t approximately equal to 8.665, which is slightly better than the one that you got for monthly. And a continuous case, this model doesn't work anymore because we are going to have this model here, okay, x0 e to the rt, and x0 is the initial amount. So let me just continue here. So you want to have $3,000, and initial amount is 1,500, and the rate is still 0.08 t. So this time I'm solving this exponential equation. Okay, so this is 8. Okay, so why don't we divide both sides by 1,500 as the way we did here, so that you have 2 equals e to the 0.08 t. Okay, and you take the ln of both sides. I'm just continuing here. ln 2 equals ln of e to the power of 0.08 t, but ln e is 1, so this is essentially just 0.08 t. Okay. T turns out to be ln 2 divided by 0.08. That's approximately equal to 8.66434. So the best way to reach $3,000 is to compound continuously. And here is the graph of different ways of compounding. As you see that in the first one, the blue one is compounding annually. I also use the time scale sort of like zoomed in a way that since all of the numbers coming out of each case is in between 8.6 and almost 9.1, I use to graph those solutions in that interval, as well as also y-axis. I put y-min to be 2970, y-max to be 3000, so that I can actually get a better outlook of these functions. So if you compound annually, that's the worst case to reach $3,000. That's almost like 9 years you have to wait for. And then the orange one is the one that you compound monthly. So this is the third fastest way to reach $3,000. As you see, it's almost like close to 8.7. And then the other two cases are pretty similar. One is compounding daily, and the other one is like continuous compounding. And to see what's going on explicitly, or to see the difference between these two cases, in fact, I wanted to zoom in more. As you see that my X-min and X-max are totally different. As you see that the red one is the continuous one. And if you do continuous compounding, you reach $3,000 the shortest time. And the green one corresponds to the daily compounding. It takes slightly longer to double your money that way. All right, this is the end of the video. Thanks for watching. I'll see you in another video. Bye.